SwayamPrabha. Digital India. Educated India.
In this problem solving session, we will be solving 4 problems on forced harmonic oscillator. These problems are taken from standard books on engineering mechanics, and I will be acknowledging along the way where I have taken them from. So, first problem is taken from Shames's book, and this is problem 19.104. It says there is a block of mass m which is pulled by a force F, and the problem states that a block of mass m is on a horizontal frictionless surface attached to a spring on a wall. When a force F equals 90 plus 22 sine of 80t is applied to it, it oscillates after the transients have died down with an amplitude of 0.5 millimeter. About a position 50 millimeter to the left of static equilibrium position corresponding to the case when there is no force present. What is the mass of the block? We will be taking a case where we can neglect the damping coefficient. So, we will be neglecting the damping coefficient. Only thing that this damping coefficient does is makes the transients go down with time, and we are talking about steady state solution. So, let us see what the problem is talking about. In this problem, I have this block, and when this force is applied, there is a force applied, then the block shifts by 50 mm from its original position, and then starts oscillating here with an amplitude of half millimeter, and we are supposed to find the mass of this block. So, it is a very straightforward calculation, because we know, as we have learnt, that when I apply a constant force, suppose I applied a constant force of 90 newtons, then the block shifts by 50 mm, and then an oscillatory force on top of it, which is 22 sine of 80 t, makes it oscillate about that position with the same frequency as the applied force, that is 80 radians per second, with an amplitude of 0.5 mm. So, first thing we can say right away that the spring constant is going to be 90 divided by 50 mm, 50 times 10 raised to minus 3, and that is 1.8 times 10 raised to 3, or 1800 Newton per meter. I will also be doing it mathematically rigorously. So, we have got this k, and then on top of it, now the amplitude of the oscillation without any damping coefficient is given by f over m divided by square root of omega 0 square minus omega square plus gamma square omega square, which goes over to f over m omega 0 square minus omega square for no damping case. So, this is given, and therefore, I can do my calculation straight away, because this is equal to f, which is given to be 22 newtons, divided by m omega square is k, which is 1800, minus m times 80 square. So, that is a very straightforward calculation, and amplitude is given to be 0.5 mm. So, let us see what do we get. We get 0.5 times 10 raised to minus 3 is equal to 22 over 1800 minus 6400 m. So, I have 0.5 times 10 raised to minus 3 is equal to 22 over 1800 minus 6400 m, or 6400 m with a minus sign plus 1800 is equal to 22 over 0.5 times 10 raised to minus 3, which is 44,000, and therefore, I get 6400 m is equal to 1800 minus 44,000. This gives m to be less than 0. Notice that when we wrote this equation, amplitude equals f over m omega 0 square minus omega square, and assume that amplitude is positive, that means the applied frequency is less than the natural frequency. And if, on the other hand, if omega applied is greater than omega 0, we get a phase difference of pi, and therefore, the equation I should be writing, because I am getting an inconsistent result that m is less than 0, which cannot happen. In equation I should actually be writing is that f over m omega 0 square minus omega square is minus 0.5 mm, and then there will be no inconsistency. So, let us solve it with that. So, I get f, which is 22, divided by m omega 0 square, which is k, which is 1800, minus 6400 m is equal to minus 0.5 times 10 raised to minus 3, or 1800 minus 6400 m is equal to minus 22 over 0.5 times 10 raised to minus 3, which is minus 44,000, and that gives you 6400 m is equal to 45,800, or m equals 45,800 divided by 6400, which comes out to be 7.16 kg. So, I solved this problem in a very qualitative manner. I first took this spring mass system and said that this constant force of 90 newtons should be shifting it by 50 mm, calculated K and then applied the formula. Let us see it in a mathematical manner also. So, the equation that we have been solving is x dot square plus omega 0 square x should be equal to the applied force, which is 90 plus 22 sine of 80t. This is the equation that we are solving. So, now I am doing it mathematically rigorously. So, the equation I am solving is x double dot plus omega 0 square x is equal to 90 plus 22 sine of 80t. So, after the transients have died down, that means whatever the small light damping is, that has done its job, the system would be oscillating with the same frequency as the applied frequency. So, it will have an amplitude A sine of 80t, and in addition it will have another coefficient B, and this I will call particular solution. The homogeneous solution, which was the 0 on the right hand side, has died down. So, particular solution should be this, and xp double dot t is equal to minus 6400 A sine of 80t. Let us substitute this in this equation out here. So, when I substitute it in x double dot plus omega 0 square x is equal to 90 plus 22 sine of 80t. For x double dot I get minus 6400 A sine of 80t plus omega 0 square, and inside I get B plus A sine of 80t is equal to 90 plus 22 sine of 80t. In writing this equation, I should also divide by mass on the right hand side, because I have divided the whole equation right from the beginning by m, and therefore, I should be writing divided by m on the right hand side. So, I have minus 6400 A sine of 80t plus omega 0 square A sine of 80t plus omega 0 square B is equal to 90 over m plus 22 sine of 80t. Now, I will equate the coefficient corresponding to the sine of 80t and the constant term on both sides, and this gives me immediately that omega 0 square B is equal to 90 over m. Omega 0 is nothing but k over m times B is equal to 90 over m. M cancels and I get B equals 90 over k. And similarly, from the other equation I get minus 6400 A plus A omega 0 square is equal to, on the right hand side I have 22 sine omega t. So, this is the coefficient. So, I get A is equal to 22 over m, 22 over m omega 0 square minus omega square. So, I have gotten B and A, and therefore, my solution for x t is equal to 90 over k plus 22 over m omega 0 square is nothing but the coefficient k minus m omega square sine of 80t. And what you are given in the problem is that this term is 50 millimeters and this term is 0.5 millimeters. The rest of the solution goes as I did earlier. So, I have shown you mathematically also how what I did earlier follows. Problem number 2. This is also taken from Shames, and this is problem number 19 times 105 from Shames. The problem is like this. Suppose I have a beam of length L which can oscillate about this middle point, and it is connected through springs to two identical blocks like this. This length is L by 2 on each side. These are identical masses m each, and this beam is made to oscillate by an angle theta t is equal to theta 0 sine of omega t. Obviously, when this beam end goes up and down, it is going to press the spring, and therefore, there is going to be a force generated, and therefore, these masses, as a result, let me write it here, these masses are going to perform forced harmonic oscillations, because the applied force is also going to be a harmonic force. And what we want to find is what should be the maximum allowed theta naught, so that the amplitude of these masses oscillating becomes less than certain number. So, let me now write the problem. A light, stiff, which we will take to be rigid, rod A C B. So, let us write it A C B is made to rotate about its middle point C, so that such that the angle theta t that it makes from the horizontal. So, let us make this angle theta t is varying as theta t equals theta 0 sine of 20 t. And then we want to find the value of theta 0 if the maximum displacement of each mass m is 20 millimeters. Maximum displacement is going to be the amplitude, and let us assume, I will write it in the bracket, assume that the whole assembly is horizontal. So that there is no effect of gravity. So, let us see what is happening. What is happening is, here is the beam, here are these masses, you are given the constant K to be 2500 newtons per meter for each spring, and the mass m is given to be 3 kilogram. So, the natural frequency omega 0 for each mass is going to be such that omega 0 square is equal to 2k divided by m, because effectively, because there are two springs, and this you can figure out yourself, the effective k is going to be 2k, and therefore, this is going to be 5000 over 3 radians per second. And as the beam moves, this distance is L by 2, theta t is given to be theta 0 sine of 20 t. So, the displacement of the end of the rod is going to be L by 2 theta 0 sine of 20 t, and therefore, the force, because the top spring is going to be compressed, is going to be K L by 2 theta 0 sine of 20 t. So, that end is being pulled up and down by that distance, and therefore, the force is going to be K L by 2 theta 0 20 t. So, if I were to write the amplitude is going to be F divided by m omega 0 minus omega square, which is equal to K, which is 2500 times L. L is given to be 1 meter. So, this is 1 divided by 2, that is the maximum force, theta 0 divided by m omega 0 square, which is 2 K, which is nothing but 5000 minus m omega square, which is going to be 3 times 400. So, this is going to be 1250 theta 0 divided by 3800, and the amplitude maximum that I want is 20 times 10 raised to minus 3. So, the equation that I end up getting is 20 times 10 raised to minus 3 is equal to 1250 theta 0 divided by 3800, and that immediately gives me theta 0 to be 0.0608 radians, which is roughly equal to 3.5 degrees. So, that is the maximum that this rod should be moving, so that the maximum amplitude of oscillation for these masses is 20 mm. You can also map this problem onto, you have seen that when you go over a speed breaker which has many bumps, your motorcycle or car, the spring in that shock absorber also starts going up and down, and then the whole thing starts performing forced harmonic oscillator. I will be making a problem like that for your assignment and giving it to you. The next two problems are from the book of Merriam. So, next two problems are from Dynamics by Merriam and Craig. So, this is problem number 3, and this is taken from Merriam's book 855. So, the problem is like this. Viscously damped oscillator has gamma equals 4.8 pi radians per second, and undamped natural frequency omega 0 equals 12 pi radians per second. Estimate range of frequencies for a force F t equals F 0 cosine of omega t, for which the amplitude of oscillation will not exceed 2 f0 over k. So, let us see what this problem means. You recall when I apply a frequency omega, the curve that gives the amplitude goes something like this. It is maximum near omega 0, and then the amplitude starts going down. So, what we want is the range of frequency such that the amplitude is not more than twice as much. So, the frequencies will lie either on the higher side, so that the amplitude is low, or on the lower side. So, the answer I should get is omega less than some omega critical or omega greater than some omega critical. So, let us now solve that. Recall that the amplitude is given by f over m divided, or f0, which is the amplitude, divided by square root of omega 0 square minus omega square plus gamma square omega square, and we want this to be less than 2 f0 over k. And therefore, this implies this f0 cancels on both sides, f0 I can cancel. This implies that 1 over square root of omega 0 square minus omega square plus gamma square omega square is less than 2 m divided by k, which is equal to 2 by omega 0 square. Switch it around and you get square root of omega 0 square minus omega square plus gamma square omega square should be greater than omega 0 square divided by 2, or I take this 2 on this side and put it here, and therefore 4 omega 0 square minus omega square plus 4 gamma square omega square should be greater than omega 0 square. This gives me 4 omega 0, this is omega 0 raised to 4, I have squared both sides. 4 omega 0 raised to 4 plus 4 omega square minus 8 omega square omega 0 square plus 4 gamma square omega square should be greater than omega 0 raised to 4, or the final equation that I get is 4 omega square minus 8 omega square omega 0 square plus 4 gamma square omega square plus 3 omega 0 raised to 4 is greater than 0. This is the equation I got to solve. I am sorry, this has to be 4, this is 4 omega raised to 4. So, the equation I have is 4 omega raised to 4 minus, let us take out 4 omega square, I get 2 omega 0 square minus gamma square plus 3 omega 0 raised to 4 equal to 0. This is quadratic equation in omega square. So, I can solve this, and therefore, if I put 4 omega raised to 4 minus 4 omega square 2 omega 0 square minus gamma square plus 3 omega 0 raised to 4 is equal to 0, I can solve for omega square, which is nothing but 2 omega 0 square minus gamma square times 4 plus or minus the square root of 16 2 omega 0 square minus gamma square minus 48 omega 0 raised to 4 divided by 2, which can be simplified to, or divided by 2 times 4, which can be simplified to 2 omega 0 square minus gamma square plus or minus square root of 2 omega 0 square minus gamma square minus 3 omega 0 raised to 4 divided by 2. And we are now given that omega 0 is 12 pi, gamma is 4.8 pi, and if you put these numbers in, you get omega square is equal to either 1.23 omega 0 square or 0.61 omega 0 square. So, the equation on top can be written as omega square minus 1.23 omega 0 square times omega square minus 0.61 omega 0 square as greater than 0. This is what I want if the amplitude has to be less than 2 f by k, and therefore, either omega square should be greater than 1.23 omega 0 square or omega square should be less than 0.61 omega 0 square. Now, you can solve and get the numbers. Finally, it comes out to be that omega is either greater than 1.1 omega 0, 1.11, or omega is less than 0.78 omega 0. You can put in the numbers and get your answers. The final problem, problem number 4, this is the answer. So, final answer is omega is greater than 1.11 omega 0 or omega is less than 0.78 omega 0. The final problem, problem number 4, is also taken from Merriam, and it's problem number 857. What it has is there is a beam on which there is a collar on which we put 2 rods, and at the end of these there are 2 masses of 0.5 kilograms on both sides. These are stiff rods, so that when this collar inside is made to go up and down, these balls start oscillating. So, the problem is stated as follows: each of 0.5 kilogram ball is attached to the end of a light elastic rod and deflects 4 millimeters when a 2 Newton force is applied on it. So, this immediately gives you the stiffness coefficient of the rod. Now, if the central collar, this is a central collar, is given a vertical harmonic movement of frequency 4 hertz, which will be equal to 2 pi times 4, 8 pi radians per second, and amplitude 3 mm, find the amplitude y0 of each ball, and I am adding from my side that after the transients have died down and take damping to be negligible. When we say damping is negligible, that means it is much less compared to omega square. So, what is happening is that if I consider each of this ball, this can go up and down like this, and what you are given is, if I apply a force of 2 newtons, it deflects by 4 millimeters, and that immediately gives me that the stiffness coefficient K is nothing but 2 Newton divided by 4 times 10 raised to minus 3, and that is 500 Newton per meter. The equation of motion when this is displaced, suppose this I take to be y, is going to be y double dot is equal to minus ky, because as it gets displaced there is a force, this should be my double dot. So, m y double dot plus ky is 0, m is given to be 0.5. So, y double dot plus k over m y is 0. So, natural frequency of this is going to be k over m, which is 500 over 0.5, which is 1000 radians per second. That is the natural frequency. Let me call omega 0 square, and after all the transients have died down, the amplitude for very negligible damping is going to be f over m omega 0 square minus omega square, which is nothing but f over m omega 0 square is k minus m omega square. So, main thing now that remains to be done is find out f. Now, let us see what is happening when this collar is moved by 3 mm. So, in this case what happens is, initially this is the mass, and as the collar moves, the position of this rod becomes like this. So, it is shifted by 3 mm, and therefore, the maximum force that it applies becomes 500, which is k, times the displacement, which is 3 times 10 raised to minus 3 newtons, which comes out to be 1.5 newtons. So, the force that we are applying now is going to be 1.5 newtons times sine of omega t. Omega we have already calculated to be 8 pi, and therefore, this is 1.5 sine of 8 pi t. This is the force. Immediately it becomes clear that the amplitude is going to be equal to f over m omega 0 square minus omega square. F is 1.5 over m omega 0 square is 500, which is k, minus m, which is 0.5, times omega square, which is 64 pi square. So, this is 1.5 divided by 500 minus 32 pi square meters. You calculate this and you will get an answer to be 8.14 mm. So, when I take this beam, there is this collar which is going up and down by 3 mm. These balls at the end of these stiff rods are going to move up and down with an amplitude of 8.14 millimeters.